Hi everybody, Cameron here. So today we're going to be looking at chapter 2, the periodic table. So we're going to be looking at the development of the periodic table, so how it came around. We're going to be looking at its structure and why it's structured in the way that it is, as well as looking at group 1, 7, and explaining the trends that we can see in the periodic table. So it's important to realize that when it comes to the 1960s, okay, or before 1969, basically, mankind only had known about 44 elements to exist. Okay, they were still discovering elements. Okay, so it came to this man Mendeleev. Now there were many people working on a periodic table, and you can go look them up. There are some crazy weird structures because people were trying to organize these elements into groups based on their properties. Okay, Mendeleev came along and he decided, well, let me organize them based on their atomic masses. Okay, but when he did this, the issue was he found that there were gaps in his periodic table, and he said that these were elements that had not yet been discovered. This was proven, however, when, now just for interest's sake, a man came up with a new element, or not came up, discovered a new element, and they gave it an atomic mass. And Mendeleev said, no, you're wrong. It's meant to be this other atomic mass. And they rechecked it, and in fact Mendeleev was correct. And Mendeleev said, yes, it's because this element is in one of my gaps on my periodic table. Okay. So Mendeleev originally organized the periodic table based on atomic mass. So he was on the right track, but not exactly right. Okay, because how we do it today is based on the atomic number. Okay, which is a bit different to the atomic mass. So the atomic mass does increase, but we do it now based on the atomic number. Okay, which is the number of protons. So looking at the modern structure of the periodic table, we organized it firstly into by atomic number. Okay, so that's the listing, is by atomic number. Okay, we then put them in various groups or columns. Okay, these columns are elements that are going to have similar properties. Okay, then we're going to put it into periods or rows. Okay, and these rows have the same number of shells. Okay, or atomic shells. We'll look at it now when we actually look at the periodic table. Okay, so the periods are the number of shells. The groups, okay, are also going to be the number of valence electrons. How many electrons they're going to have in the outer shell. If you remember from our previous lecture, calcium had 2. Okay, so I can already tell that it has in group 2 because it had 2 electrons in its outer shell. We call that the valence electrons. Okay, now if you remember from the previous slide, we said that all atoms are trying to get a full outer shell. Now this means that they are either going to gain or lose electrons to do that. Okay, so from group 1 all the way to group 3, okay, it is going to be easier to lose either 1 electron if you're in group 1, to lose 2 electrons in group 2, to lose 3 electrons if you're in group 3, than it is to gain those electrons. Okay, so all of those elements in all those groups are going to become positive ions because they're going to lose their electrons. Okay, whereas in group 5, 6, and 7, okay, it's easier for them to either gain 1 electron, gain 2 electrons, or gain 3 electrons to become negatively charged ions. Okay, group 4, it's a bit of a weird one. That's stuff like carbon, okay, and we'll get to that later, but it usually shares these electrons and gains them. Okay, so it doesn't lose them or just gain electrons. It's usually going to sort of share them. Okay, our metals versus our non-metals can also be seen in our periodic table. Metals are malleable, which means they can move, okay? They can conduct electricity. We'll get to that when we do bonding. And non-metals are usually insulators and kind of brittle, okay? Then we have our noble gases. Our noble gases are in group 8. Group 8 meaning they have a full outer shell, so they don't need to gain or lose electrons, okay? And they're quite stable. They don't bind to other atoms. Okay, so looking at the modern periodic table. As we can see here, let me get my pointer out. As we can see here, it goes up by the atomic number. Okay, so starting at hydrogen with 1, going to helium, 2, lithium, beryllium, boron, carbon, nitrogen, each going up by 1 proton. In the earlier lesson, as I mentioned, I think in the first one, I mentioned carbon, okay, from your pencil. If it had to gain 1 proton, it all of a sudden becomes nitrogen gas. That's how much of a difference just gaining 1 proton can do to the property of an element, okay? So now we know that they increase by 1 proton, okay, to get the sequence. We then got to look at why they put them in groups, or these columns, okay, and periods and rows. So we mentioned that periods indicate, so the periods going across, let me just get this. So our periods going horizontally, okay, represent the number of shells that you get. Okay, so aluminium, I can already tell aluminium is in period 3 because it has 3 shells. And if we go to period 1, 2, 3, here we see aluminium. Okay, 3 shells. Oxygen has 2 shells because it's in period 1, 2. So 2 shells in oxygen means it's in period 2. Nice and easy. Okay. Now when it comes to our groups are going to tell us how many valence electrons, how many electrons there are in the outer shell and the outer energy level. Okay. So something like aluminium is going to have 1, 2, 3 outer electrons in its outer shell. Okay. Now, when it comes to the periodic table, how we usually group this thing is by going group 1, group 2, the transition metals. Okay, we usually put them under group 3 because usually they're going to have 3 electrons in their outer shell. Sometimes they can have 2. It depends, and we'll get there. Okay, but for now I want you to forget about the transition metals. 1, 2, 3, 4. Okay, so something like aluminium has 1, 2, 3 valence electrons in its outer shell. The electron configuration we can see here is also 2, 8, 3. Okay, and therefore it is going to lose 3 electrons to get a full outer shell from the previous shell. Okay, the same thing with oxygen here. Oxygen is going to have 1, 2, 3, 4, 5, 6. Therefore, it's in group 6. 6 to get to 8, it's going to gain 2 electrons. And that means it's going to become a negative ion with O negative 2. Okay. So from the top, periods, horizontal, are going to be the number of shells. Groups are going to be the number of valence electrons, the number of electrons in the outer shell. They are all trying to get to 8 electrons. Okay, and groups 1 all the way, and including transition metals, to group 3, it is going to be losing electrons, okay, and becoming a positively charged ion. Whereas groups 5, 6, 7 are going to easily gain electrons to get their full amount. So 7, okay, all these in group 7 are going to just need 1 more electron, so they become negative 1, and now they're going to have a full outer shell as well. Notice it has a 0 here because it is not charged, because it has full amount of electrons in group 8. Okay, I hope that makes sense to you. So it's important to understand this. because a lot is going to be based off of this idea. So make sure you understand your groups, what they mean. If I tell you magnesium, okay, what is magnesium going to need to get to 8 electrons? It's going to need to lose 2 electrons. Okay, so it's going to have become a positive ion of +2, you see. Okay, so looking at the groups in the periodic table, we're going to be looking at 3 of them, and they're quite extremes to one another. So firstly, we have the noble gases. Noble gases are in group 0 or group 8. Okay, they have 8 electrons in their outer energy level. They're very stable. They can exist on their own. Okay, so you can have one neon atom, let's say. Okay, whereas your other gases, okay, such as chlorine, oxygen, nitrogen, hydrogen, if they are on their own, if it is just oxygen, it'll never just be O. It'll be O2 or H2 or Cl2 or N2. You see that they bind with each other. Okay, we call them diatomic molecules. But when it comes to noble gases, they can exist on their own as singular atoms. Okay. When it comes to alkali metals, quite the opposite. They are very reactive. Okay, and why is this? Because group 1 is alkali metals. Okay, and in group 1 they only have 1 electron in their outer shell. Okay, so all they need to do is lose that 1 electron, and they're going to be stable, and they're going to have the full number of electrons in the outer shell, which is what they want. So they will become positively charged by 1, so +1. Okay, and if you remember from our last lesson, as you get further away from the nucleus, the amount of energy in those electrons on the outside is a lot higher than the electrons on the inside. So as our atom increases, okay, as we go down the periods here of this group, our atoms become bigger and bigger. It goes from 3 protons, 11, 19, 37, they're getting bigger and bigger, and therefore their electron shells are going to get more and more. Okay, because remember, each period is going to be the number of shells. Okay, so lithium, okay, is going to have a lot less shells than Rb. Okay, and what's going to happen is that they're going to become more and more reactive as that 1 electron on their outer shells is going to keep gaining energy as we go further down this group. Okay, they're going to be quite soft, and they have a low density. You can cut sodium, with a plastic knife if you want to, but they are very reactive. You put them in water, they're going to create fire and smoke and react quite violently, okay, to create hydrogen gas. Okay, it's also going to create a basic pH, which is quite a high pH due to that OH, the hydroxide, being created as well in the solution. Okay, and they're going to have quite a high boiling point and melting point. Okay, so opposite side of the spectrum, we have the halogens. Halogens are in group 7, which means they have 7 valence electrons. They have 7 electrons in their outermost shell. This means that they only need to gain 1 electron to become stable and to have that full outer shell of 8. Okay, now they are going to usually have a very low melting and boiling point. Okay, but this is going to increase as we go down the column. Okay, now this makes sense because they are then going to become less reactive as they go down the column. This is only for group 7. Okay, if you remember, in alkali metals they became more reactive. Okay, but that's only because they were trying to give away this electron. But in group 7 they are trying to only gain 1 electron. So if the atom gets bigger and bigger and bigger, okay, the outer shell is still going to, even though it has a lot of energy, be more stable. Okay, because it's going to have a lot more shells around it as it goes down the period. So that's why fluorine is going to want that 1 electron a lot more than chlorine, bromine and iodine. Okay, in that order. And to gain that electron, they are usually going to form covalent bonds with other nonmetals to share it, such as hydrogen chloride. Okay. And then yes, we talk about those diatomic molecules, so it can form covalent bonds with itself as well. Bromine, chlorine, fluorine, they're all going to be diatomic molecules. And we'll get to displacement reactions, I think, later on when we do organic chemistry. But basically, these reactions can break double bonds because they only require one more electron. Okay, so just to recap, as we go down periods, the number of shells is going to increase. Okay, what this means for group 1 that needs to lose one electron is that they become more reactive as the energy level increases. The amount of energy in that outer electron that needs to be released is going to increase. Okay, making it more reactive, making it more ready to ditch that electron. Okay, now the opposite can be said for our opposite side of the periodic table in group 7, our halogens, okay, where they need to gain one electron, and the further down the group we go, okay, so as the periods increase, the number of shells is going to increase, and therefore it's going to become more stable and less reactive. Okay, so our final group that we're going to be looking at when it comes to periodic table is the transition metals. Okay, so these are good conductors of electricity because they're going to form metallic bonds with each other. We'll get to that later. They're very hard and strong. They have a high density and a very high melting point. Okay. The chemical properties are that they're not very reactive, but they are still reactive. Okay. They usually require heat to react or water with oxygen. Okay. This happens with something like rusting usually. So when we say that they are kind of reactive, it's usually rust. Okay. So oxidation. Copper does that. Go look at the Statue of Liberty. What color she originally was. She's not green. Okay. And rust in general. Okay. If you have iron, oxygen, and water, it's going to form iron oxide, which is rust. Okay. And this is what I was saying earlier. The ions that can form for one element can sometimes be positive 2, sometimes be positive 3. And that's why I didn't mention them when we were talking about the periodic table before. All transition metals are like this, but luckily they're going to tell you. They will indicate for you what type of charge a specific element will have when it's a transition metal. They don't do this for all elements, only transition metals. It'll be Fe2 if it's a positive 2, or it'll be Fe3 if it's positive 3. Okay. So yeah, please, if you don't understand this, go over these notes again, go over the videos again, and if you still don't understand it, please book a class with me, and I will go through this with you. We can do examples, because this is the basis of the entire section, okay, this entire subject, really, is to understand this, okay? So please make sure you get it, and if you don't, let me help you, okay? Come book a class. Okay guys, we'll see you in the next lesson.